Sorry for delaying, sir. I
Come,
forgot to make it.
come on. Okay, students, let us start. Sorry for the delay. To record now.
Recording in progress.
Yes, we will catch it up on another day, the 10 minutes lost, okay? We did determinants last time, and we said for a 2 by 2 determinant, it's elementary. A, B, C, D, these are real numbers that we are considering, but even for complex numbers, you can do this. This is equal to AD minus BC. AD minus BC. So we did an example for that also last time. It's very elementary, no? 2 by 2. When it comes to 3 by 3 determinants 3 by 3, how do you expand it? 3 by 3 determinant, let us write it as A11, A12, A13. I couldn't complete the example we started last time. A22, A23, then A31, A32, A33. Now, this is how we do it. We first use a sign convention. Now, what do we mean by this determinant? Determinant is a number. Okay, it's a single number. You can think of it as a notational convenience. So, if you are given a 3 by 3 matrix, we can talk about its determinant. It's intimately connected to the properties of the matrix. Determinant of a matrix is connected to the properties of a matrix. So, this gives us an easy way to figure out whether a matrix is invertible or not. Whether the inverse of a matrix exists or not. All you have to do is check the determinant, and if it is non-zero, A is invertible. So let us first learn how to expand this. Sign convention is this. If you take ijth place, we use if I plus j is even, we assign a plus sign. That is for expansion purposes. If it is odd, I plus j is odd, we assign a minus sign. If I plus j is even, plus, and if it is odd, minus. Okay, so what is the sign that should be assigned to this place? A11. 1 plus 1 is even. So we put a plus on top. And here 1 plus 2. I plus j, no? Aij. If you take Aij entry, the sign convention is this plus this odd. Therefore, we consider that as with the minus. This one even, consider with that. It's a very elementary. We can this way place is always plus. Then alternate signs: plus, minus, plus, minus, plus, minus, plus, minus, plus, minus. That is how it goes. I only need, so I'm going to give the expansion using the first row. This is, I'm trying to expand this. I will expand it using the first row. First row expansion. First row expansion is this, right? This is equal to, write this term with the sign. So that is A11. After that, delete the row and column containing that entry. Delete the row and column containing A11 entry. What is left? What you see is a 2 by 2 determinant. A22, A23, A32, A33. So This is the way to expand. So with the sign A11 and then this determinant of that. A22, A23, A32, A33. Then that is the first piece. Contribution to the determinant from the first entry. We are expanding using first row. So the sign convention is used only for the first row. If it is the second row expansion, we shall do in a minute. Similarly done. So now go to the second one. Minus, write it as minus A12. Determinant obtained by deleting the row and column containing that. That is displaced. So this row should be deleted, this column should be deleted. Do it mentally. What is left? A21, A23, A21, A23, A31, A33, A21, A21, A23. Then A31, A33. Plus, then go to the third term. Okay, if it is n by n matrix, we do it for every entry in that row. So plus A13 plus A13. What is the subdeterminant? A13. Delete the row and column containing the two. What is left is A21, A22, A31, A32. A21, A21, A22. Then A31, A32. A31, A32. That is how you expand. This is A. That is how you expand a determinant. Now we can. This is a 2 by 2 one, so you know how to expand it. Okay. That is A22, A33 minus A23, A32. That is the expansion.
Recording stopped. Recording in progress.
Students, can you see the screen?
Yes, sir.
Okay.
Not the screen, sir, but you.
When a hole comes, that happens. Okay, students, let us start with the. Let me check the recording also. Yes, it's recording. Yes. Let us do the problem we started last time, 032. Expand this determinant. Okay, so determinants are there for every square matrix. All you do is, instead of the matrix notation, you use the determinant notation. The definition of this gadget is given here. First row expansion. Let us now try to do this. This is equal to. So sign convention. Plus, minus, plus. Okay, just keep that there. You don't even have to write them. 1 times 1 times the 2 by 2 determinant obtained by deleting row and column. That is 5132. Okay? Subdeterminant is 5132. 5132. Then next one is minus 2. It's written, it's 2. The sign convention comes in and makes it minus 2. Then the row and column containing that term would be deleted. So what is the 2 by 2 determinant you see? Minus 1, 1, 0, 2. Minus 1, 1, 0, 2. Then third one, plus 3. Plus 3 times, you can see it here. No, this is the determinant. The row and column containing 3 should be deleted. So try to do it without doing anything like this. You can mentally do it, but if you think you would make a mistake, do it. So 3 minus 1, 5, minus 1, 5, 0, 3. Do you all understand it? This is equal to, now get the value. How do you find it? This is 10 minus 3. 10 minus 3. Here minus 2 times, what is that determinant? Minus 2, this is 0. Minus 2 minus 0. Plus 3 times this determinant, multiply these two, minus 3, then subtract this. Minus 3 minus 0. So this is 7, this is plus 4, 7 plus 4, here minus 9. 7 plus 4 minus 9, so that is equal to, this is 11, 11 minus 9 is equal to 2. So that is the value of the determinant. Now, first thing to know is that we can expand the determinant using any row or any column. Use the sign convention. This is the sign convention. Sign convention. Sign convention is used only for the row or column that we use in the expansion. So let us now see, this is the first row expansion is what we have given there. Now let us try to do the second column expansion. For this one, first row expansion, let us mention that first, and a determinant can be expanded using any row or any column. You get the determinant can be expanded using any row or any column. You get the same answer. The value is the same. Value is the same. Regardless of, we can do it for general 3 by 3 matrix. You expand it using any column and see that the answers are the same. Meaning here the answer we did not complete it. It is A11, A22, A33 minus A23, A32. Those terms you get here 2 terms, 2. There are 6 terms. Those 6 terms are the same. After simplification, whichever row or column that you use. So let us go to this cell. Here I have done it using the first row. First row expansion. I got the first row expansion. I got 2 as the value. Okay, now let us do the same thing here. Yes. Value is the same. Now, take the same matrix. Expand it using the second column. 1, 2, 3, minus 1, 5, minus 1, 5, 1, 0, 3, 2. Expand using the second column. Expand using the second column. Expand using any row or any column. You must get the same, you get the same value. We can prove it in general by expanding, at least for 3 by 3, by expanding using the second column. Here, we shall understand it using this example. Go to this example. Now, sign convention. This is always a plus. Then this is minus, here plus, minus. That is the sign convention. If you consider, yeah, I should. That is using this I plus j, even plus I plus j or minus. Say for example, this place, this is 2, 2 place. 2 plus 2 is even, therefore plus. Here 2, 1 place. Sorry, 1, 2 place. 1, 2 place. First row, second column. 1, 2 place. 1 plus 2 is 3. Odd, therefore minus. Here, this is 3, 2 place. 3, 2. 3 plus 2 is 5. Odd, therefore minus. You don't have to do that. This is plus, then sign alternates. Sign changes alternatively. If this is plus, this is always plus. Then this is minus, plus, minus. Expand it using this. This is equal to, so first entry, minus 2. Minus 2 times, how do you expand it? The same way as we did earlier. Row and column containing those two. Deleted. This 2. Row and column containing that. Minus 1, 1, 0, 2. Minus 1, 1, 0, 2. Then go to this one. It is plus. Expand using the second column. Plus 5 times row and column containing those. So you see 1, 3, 0, 2. 1. So this and this deleted. Row and column containing this entry. That and this. 1, 3, 0, 2. 1, 3, 0, 2. Then last one, minus 3. I'm expanding it in this column. Minus 3. What is the subdeterminant? Can somebody tell me? Minus 3. Row and column containing 3. That entry should be deleted. 1, 3. Yes?
Minus 1, 1.
Very good. This one and this one should be deleted. So 1, 3, 1, 3, minus 1, 1. Now expand it and see. This is equal to minus 2. 2 by 2 was here. You get minus 2. The other one is 0. No? Here plus 5. Plus 5. This is 2. This is 0. This minus this. Here minus 3. Here 1 minus minus 3. 1. The product of these two is 1. Product of these two is minus 3. So it becomes plus 3. Minus minus 3. So this is equal to minus 4 plus 10. Here minus 9.
Plus 4, sir.
Something wrong. Yes. Yeah. What is it? Plus 4. Yes. Plus 4. Plus 4. Still something is wrong. No? What was the answer we got earlier? 11 minus 9. 2. Minus?
Then 1 minus 3, sir.
What's another?
Antima varahana.
Antime ke 1 minus 3 ne enne metana. Oh, 1 minus minus 3 can 1 plus 3. Yes, this is 4. No?
Minus 12, sir.
Yeah, minus 12. Minus 12. Now it is 14 minus 12 is equal to 2. So last time, last way also, we got the same answer. So that is to explain this important thing about expansions of determinants. A determinant can be expanded using any row or any column. You get the same answer, same value. Okay, I did it only for example, but you can do it for this and see that it is true in general. There are 6 terms coming. Those 6 terms are the same after rearrangement of terms. Whether you use any row or any column. So that is the first thing. And so I think I gave this last time, but again we shall mention. Let capital A be an n by n matrix. The determinant of A, we give 2 types of notations. The determinant of A, the determinant of A, the notations are, some people write, we use this also, dit A. And some people use this absolute value type notation. Both means the same. The determinant of A, there are 2 notations. When there is a matrix, I will use dit A to mean the determinant of A. So, right. Now, properties. You understand what I said here, no? So, suppose let capital A be the matrix 2, 3, minus 1, 5.
Open.
Thank you. Let A be this. Dit A again, what is dit A? Dit A is 2, 3, minus 1, 5. Okay, so this is the same as this notation. So take the matrix and make it a determinant by putting 2 vertical bars. So 10 minus 10 plus 3, that is 13. So that is just to tell you about this notation. If you have a matrix, n, it should be square. Determinants are always square. N rows, n columns. Determinants are there only for square matrices. These gadgets are there only for, you can have 4 by 4, 4 rows, 4 columns. Same way, expansion is done in the same way. Sign convention and use the row and column containing the entry. Delete the row and column containing the entry and multiply the entry with the determinant obtained by that with the sign convention. So, properties of determinants. First property, dit A is equal to dit A transpose. Dit A is equal to dit A transpose. What is transpose? Transpose is the transpose of a matrix is the matrix obtained by interchanging rows and columns. Dit A is the same as dit A transpose. If you want, you can prove that. At least proofs for 3 by 3 is enough, okay? It is valid for any order. This is any, let A be any square matrix. Then dit A is equal to dit A transpose. Let us try this for 3 by 3. Otherwise, you will be just memorizing it. No. So let us take A to B, A11, A12, A13, A21, A22, A23. We could have used A, B, C, D, E, F notation also. A31, A32, A32, yes, 33. Let us take A to be that. So what is A transpose? So dit A is just this. A transpose, then A transpose is equal to, how do you get the transpose? You interchange the rows and columns. First row becomes first column of the transpose. First row is A11, A11, A21, A31. First row became first column of the transpose. Second row becomes second column. A21, A22, A21, A22, A23. That is the second row. It became the second column. Third row is A31. It becomes the third column of the transpose. A32, A33. That is A transpose. Now what we are saying is our first property is determinant of a matrix is equal to the determinant of its transpose. Okay? Now all you have to do is expand this using the first row. Okay? So dit A. Underneath this I can write dit A. Dit A, first row expansion, A11. So determinant is, so this now, I didn't write it, I straight away imagine having the determinant notation there. Dit A is equal to A11 times A22, A23, A32, A33 minus A12, we have written this now, A12 minus, because this is plus, first row no, minus plus, A12, A21, A23, A21, A23, then what is the entry? This one, no? So A21, A23, A31, A33. And then plus that the other term is there. Okay, so let us, you write this, okay? Now, that is using the first row expansion for A. To see that they are the same, go to A transpose. What is dit A transpose? Dit A transpose. A transpose is this no? So dit is that. There is this and this. Without wasting time, we can straight away write dit A transpose. Now we use the first column because first row of this is first column of that. No? So therefore, using first row, this is the expansion. You can multiply and write the answer, but I didn't do that. I'll let you do it. Okay. Here, first column. Expand A transpose using the first column. What do you see? First column, this is plus, minus, plus. Sign convention. And now expand. This is equal to A11 times row and column containing that is deleted. That is this part then. A22, A32. Here, A23, A33. Then minus A21, row and column containing that. So, deleted. A21, first A21, A31, A32, A33, A21, 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 A31. Then A32, A23 rather, A33, 23, A33, plus the other term. Plus the other term, that is A31. Same thing here also. What is this? A transpose. Here I have made a mistake. No? What is the first column? First row becomes the first column. A11, A12, A13. A13. Haridban second now. A22, second column. A21, A22, A23. Hari. Third row, A31, A32,
Column
A33.
A1 2.
First.
First column second A1 2.
Second A12. Yes. First row first column A11, A12, A13. So the method effect පළවෙනි එකට නෑ නේද? A22, A32, A23, A33. ඒකට නෑ. But for this one, there is a change. That also okay. Minus A12, not 2. I'm expanding using the first column, A12. So what is the leftover determinant? A21, A31, and then A23, A33. Then the last one you can write. Now here, that is dit A. Dit A, what is the first term after expansion of dit A? A11, A22, A22, A33 minus A23, 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 A32 minus A12, then there is this, and then there is the other term. Okay, now look at this one, expand this and see. What do you get? A11 times A22, A33. A22, A32. Here, these two are interchanged, but A23, A32. A23, A32, same thing after multiplication. A22, A33 minus A32, A23 minus A12, this, and then plus. අයියෝ පේන්නේ අර එක්සර්සයිස් එකේ ඉස්සෙල්ලා කිව්ව හයි එකකින් හොඳයි කියන්න. A11, so this is this minus this. Now these two are the same. That is the expansion of the first. That is the first row expansion of dit A. Here, first column expansion of dit A transpose. These are the same. So these two will be the same, and these two will be the same. So therefore, conclusion is that dit A, we proved it for 3 by 3, dit A transpose. So that is the important thing you have to understand. If you take a determinant and take its, matrix and take its transpose, determinants of both are the same. That is the second property that, that is the first property that we give. Okay. Then the second property. Second property is if you interchange, second property under properties, If you interchange any two columns or any two rows of a determinant, you pick up a minus sign. Let us say, let capital B be the matrix. Let capital B be the matrix obtained by interchanging any two rows or any two columns. Obtained by interchanging two rows, any two rows, inside brackets say two columns. Valid for both any two rows or any two columns of capital A. At the very top we said capital A is n by n matrix. Then the property is dit B is equal to minus dit A. Dit B is equal to minus dit A. Let us example. You do this. Example. Let capital A be say 1 0 minus 1 2 1 0 5 minus 1 1. And let B be. So you find the matrix determinant there, and then let us say B. Let us interchange first row and the second row. Interchange those two rows. B is 2 1 0 1 0 minus 1. Last row keep it the same. 5 minus 1 1. Here this row, and this row, we have interchanged them to get this one. We have interchanged, second row became the first row. Same thing can be done for any two columns also. What does the theorem say? Then dit B is equal to minus dit A. So you can verify this for this. Find the determinant of this. Find the determinant of this after changing to first two rows, first row and the second row. Then dit is equal to this. Verify this. Okay, homework. Verify this. What is verify? Show that it is true. Verify this. Show that it is true for this by using computation. Find dit A, find dit B. If this is 5, this will be minus 5. So it is a verification of this property. That is the second property. Third property, if any two rows, or just say two rows, if two rows, inside brackets, two columns, or two columns. MNS. If two rows or two columns of a matrix of A, square matrix A, are equal, then dit A is equal to, dit A is equal to 0. Dit A is equal to 0. Let us take, let us verify this for 2 by 2 matrices. If two rows or two columns of a matrix are equal, then its determinant is 0. So let us take the 3 by 3 case. Let us write A, B, C rather than A1, 1. Remember, I made a mistake earlier also. A, B, C, D, E, F, and this is again D, E, F. So two rows are equal. This row and this row are, these two rows are equal. So what are we saying? If two rows are equal or two columns are equal, here two rows, then then value of the determinant is 0. It's easy to see. Take a row, okay, here only 3 by 3. No? So these two are equal. Expand using the first row. Plus, minus, plus. Expand this using the first row. What do you get? A times, you can straight away write the determinant value, but A times EF, minus B times, DF, then plus C times, row and column, DE. But this is equal to EF minus EF, 0. DF minus DF, 0. DE minus DE, 0. So therefore, the entire thing becomes 0. Okay? So if any two rows are equal or any two columns are equal, then the value of the determinant is 0. Property. Now, property, fourth property. Okay, just need. Fourth property. If a row or column, if a row inside or a column, if a row or a column of A consists of zeros, then needless to say, dit A is equal to 0. If it has a 0 row or a 0 column, for 3 by 3, let us say A, B, C, 0, 0, 0, E, A, B, C, E, F, G, it doesn't matter. Take this. How do you show that this is 0? It's a determinant of a matrix containing a 0 row. Expand using the second row. Equal to 0. 0 times something minus. So this is plus, minus, plus, minus. But it is 0 times. Minus 0 times something. So it is 0. Plus 0 times some subdeterminant. So again. So 0, expand using the second row. If you do that, you see that answer is 0. So now, fifth property, if you take a matrix and multiply any row or any column by a constant, then the value of the determinant also gets multiplied by that value of that constant. So fifth property, let capital B be the matrix with the matrix obtained by multiplying a row or a column by multiplying a row or a column. Multiplying a row or a column of a matrix A. These are all square. Okay, we are talking about determinants now. Then did B is equal to K times did A. K times did A. So how do you multiply? For matrices, if you multiply a matrix by a constant, every entry gets multiplied by that constant. But if you multiply a determinant, see here, determinant by a constant, means that you multiply either a row by that constant or a column by that constant. So let us say example a squared, a cubed, b squared, b cubed, c squared, c cubed. A, B and C are numbers, real numbers. Now, from this column, every entry is multiplied by A, no? A is a factor. So I can factor A out from the first column. B is common to second column, B, and C is common to the third column. What is the matrix after that? This is equal to A factored out. So if a matrix, so A times, okay, use this 1A squared. What did I do? From this column, I factored out A. Because if you multiply a column or a row by a constant, determinant gets multiplied by that. So I have used that property. K is A for the first column. And you can write the rest, and then you see that B is common for the second column, so factor B out. C is common to the third column, factor. So A, 1, B, 1B, here B cubed. B squared. Last column, C is common, 1C, C squared. Now, how do you expand this? It's this matrix can be expanded easily. These entries are equal, so I can make, using column operations, I can make this 0 and this 0. After that, you can find the value. So we will come to that later. That property is not done yet. No? So that is how we use this property. So unlike for matrices, if you take a matrix and multiply by a number, every entry gets multiplied. But if for a determinant, if you take a determinant and multiply by a number, a column or a row, then its value gets multiplied by that. See, you understand this, no? A squared, A cubed. A is common to this, so I can factor A out. Because after, if you want to put this back, multiply by A, any column. So take this column and multiply by A. A squared, A cubed. B, multiply the second one by B, second column. Multiply the third column by C, you get this back. So that is how you work with constant multiples of determinants. Now, some easy. If a matrix is a diagonal matrix, what is the it's 9. So we shall stop there for today, and we shall finish the determinants on next Tuesday. I told you this twice. I think I will send the tutorial tonight. So regarding last one for matrices and determinants. I will include determinants also in the team. So that is why it was delayed to cover the material we cover under determinants also. Okay. So sorry for the delay. I will catch up the lost time on a later date. Okay. Right. See you on Tuesday. Not Tuesday, Wednesday. Sorry. Wednesday. So, bye for now.
Thank you, sir.
Thank you, sir.
You are welcome.